How's everybody doing out there? Well, hopefully everybody did a great job with Chapter 8 and our one variable hypothesis testing. So in this section, we're going to be doing hypothesis testing with two variables. So instead of having a single sample mean, we're going to have two different sample means. And so when we're comparing things, we aren't necessarily going to compare, like a claim won't be mu's greater than 20. What we're going to be doing is comparing a mu from one sample to another. So it could be that we're comparing like Starbucks to Dunkin' or Pepsi to Coke or something like that. So we won't actually be comparing a mean to a number, we're going to be comparing a mean to another mean. Now, the good thing is, for the most part, everything that we've worked on is very, very similar to what we did for our hypothesis testing in Chapter 8, other than the fact that we're going to have the two samples. And so if we look at the conditions for Chapter 9.1, we're testing a claim with two means, and again, the sigma is known. So this is going to be very similar to what we did in 8.4. So since our population standard deviation is known, that means we'll be working with z-scores, inverse norm, normal CDF, things like that. All right, so let's take a look at our conditions that we need. So notice in step one, instead of comparing mu to a value, now we're actually comparing mu1 to another mu2. And so again, so there won't be any numbers in our claim. We're always going to be comparing the population mean of one thing to the population mean of another thing. But otherwise, all the same conditions are true. So our not equals claim goes with our equals. Our greater than claim is going to go with our less than or equal to. And our less than is going to go with our greater than or equal to. So step one is more or less the same, not too much different. Now for step two, so when we're going to find our z sub t score, so notice in this case, instead of subtracting the sample mean from the population mean, now we're actually subtracting the two sample means from each other. And since we have two samples, we have to have both standard deviations in there as well. So notice we're taking the square root of the first standard deviation squared divided by the number of things sampled in that first set, plus the standard deviation squared divided by the number of elements in that second sample. All right, so our z sub c, our z comparison, is going to be exactly like we did before. So we've got our inverse norm. And again, it's going to be either alpha if it's a one-tailed test, or alpha over 2 if it's a two-tailed test. And then again, 0 and 1 for those guys. All right, so step 3, so again, almost exactly the same as what we had before. So we're going to be using normal CDF in our two-tailed test and making sure we multiply that by 2. So we've got our multiplied by 2, since our alpha is going to be divided in half and covers both the left and right hand side of our normal curve. And then our two one-tailed tests, again, just plain old normal CDF. And again, depends on whether it's a greater than or less than. So notice for our greater than, our z sub t is our lower bound. For our less than, our z of t is our upper bound. And then finally, step 4, same as pretty much every hypothesis test we've done up to this point. If p is less than alpha, we reject h naught. If p is greater than alpha, we're going to fail to reject h naught. All right, so let's just dive in and look at an example and see how we do. All right, so for example 1, we're comparing two different engines. So the mean RPMs of two competing engines are to be compared. 10 engines of each type are randomly assigned to be tested. Both populations have normal distributions, and the following table summarizes the details. So engine 1 has a sample mean RPM of 1500 with a population standard deviation of 80. Engine 2 has a sample mean of 1600 with a population standard deviation of 90. Does the data indicate that engine 2 has a higher mean RPM than engine 1? Test at the 5% level of significance. So now the key to this one is, since we've got two different samples, we're going to have to call one of them like mu1, one of them mu2, one of them x bar 1, one of them x bar 2. And so you can do them in any order. So in this one, since engine 1 was first and engine 2 was second, since they already have the 1 and 2 there, I'm going to kind of go with that style for these. So I'm going to think of engine 1 as my mu1 and my engine 2 as my mu2, which means that my 1500 is going to be my x bar 1 and my 80 is going to be my sigma sub 1. And then my engine or sample mean 2 is going to be 1600, and my population standard deviation 2 is going to be 90. All right, and so for this one, we are testing them at the 5% confidence level, so that's also going to be our alpha for this case. So our alpha is 0.05. And then in the very beginning, they talked about 10 engines of each type were looked at. So in this case, we've got N1 is going to be 10 and N2 is going to be 10. Now, they don't always have to be the same. The sample sizes can be totally different for these. This one just happens to be the same, but that's not necessarily true. All right, so now that we've identified everything, so we need to write down our claim. And so we do want to be a little careful of our claim because according to this, it says engine 2 has a higher RPM than engine 1. So from an inequality perspective, this is going to look like mu2 is greater than mu1, which is in fact true. But whenever we're setting up our claim, we always want the mu1 first and then the mu2 second. So if we want the mu1 first, then this is actually going to be written as mu1 is less than mu2. And then our null hypothesis is going to be that mu1 is greater than or equal to mu2. All right, so perfect. So again, remember when we're writing our claim, we always want mu1 first, then mu2. Otherwise, it'll mess up our graph and everything else to go with it. So, all right, so now let's go ahead and focus on our test statistic. So again, just to remind us what our z sub t looks like. So we're going to take sample mean 1 minus sample mean 2, all divided by the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And again, all that stuff's inside the square root. So our x1 sample mean is 1500. Our x2 sample mean is 1600. Our 80 was our first standard deviation divided by 10, plus our second standard deviation, 90 squared, again, all divided by 10. And so we want to go ahead and type this in the calculator. So we do want to be careful how we type this in the calculator, so I'm going to demonstrate it to make sure we get it right, because it's easy to make a little mistake here. All right, so we've got our top numbers. So again, we want to make sure we put parentheses around our top numbers. So 1500 minus 1600 divided by the square root. And so again, I'm going to put some parentheses in here. So my 80 squared divided by 10 plus my 90 squared all divided by 10, and then close the parentheses, and then if we hit enter, so it looks like our z sub t is negative 2.62, or 63, sorry. So our zt is negative 2.63. All right, perfect. And so again, notice our claim was mu1 is less than mu2, so that's why we've shaded to the left-hand side. And so again, that's why it's really, really important that we always set up the mu1 first and then the mu2 second to make sure we get our drawing correct. And so with this one, since it's a one-tailed test, alpha is this whole entire 0.05. Just like before, if we land in the shaded section, we're going to reject H naught. If we land in the white, we're going to fail to reject H naught. So let's look at our Z comparison here. So we're going to do inverse norm of our whole alpha divided by 0 divided by, or comma 0, comma 1. And so if we throw this in the calculator, inverse norm of 0.05, comma 0, comma 1, and we end up with negative 1.64. And since our alpha is on the left-hand side, we actually do want to keep the negative this time. So we're looking at negative 1.64 is the dividing number between the reject and the fail to reject. And so negative 2.63 is going to fall somewhere in this area. So since it's in the shaded region, it looks like we are going to reject H naught, which looks good. So now to verify that, let's go ahead and do our p-value. So we're looking at normal CDF. And so with this one, since it's shaded to the left-hand side, then our z sub t is going to be the upper bound. And so we need some ridiculously small number for our lower bound, negative 2.63, and then our 0, comma 1 again. So throwing this in the calculator, normal CDF, negative some really small number, comma negative 2.63, comma 0, comma 1. And so we end up with 0.0043 for our p-value. 0.0043, which is definitely less than our alpha of 0.05. So our p-value supports our graphing method above. So again, for both cases, we're rejecting H naught. So this looks good. So it appears that our claim that engine 2 has a higher RPM than engine 1 is in fact true. So we reject H naught. There's sufficient evidence to support the claim. Engine 2 has more RPMs than engine 1. All right. So again, not that much different. I mean, really, the claim's kind of the biggest different. The z sub t obviously is slightly different, but the inverse norm, p-value, the way we shade the graph, all that other stuff is exactly the same as what we did in Chapter 8. So for this one, I think I've only got one practice problem for this kind. So go ahead, everybody work on this one practice problem, and then we'll come back and we'll look at 9.2, which is going to be the one that's going to occur probably most often. So good luck, everybody, and if you have any questions, just let me know.